This is the chat session for MGF 1107, Liberal Arts Math 2 for Florida Southwestern State College. If you're a student from another college, you're more than welcome to listen and observe. Those of you that are my students, please let me know if you have any questions on any of the concepts. I'll be glad to assist you. This is in reference to the textbook sections 15.1 and 15.2. A graph consists of a finite set of points. Vertices are points on a graph, singular version vertex. Edges are line segments or curves of a graph. A loop is an edge that starts and ends at the same vertex. Not every point where two edges cross is a vertex. We always indicate vertices by black dots, as you can see in the drawing below. Where AC and BD cross, you'll notice it is not a vertex. Two graphs are equivalent if they have the same number of vertices connected to each other in the same way. Placement of the vertices and shapes of edges are unimportant. You'll notice we have two graphs here. Both have vertices A, B, C, D. Both have edges A, B, B, C, C, D. Therefore, they are equivalent. Degree of a vertex. This is determined by the number of edges at that vertex. So therefore, A has degree 5 and C has degree 2. A vertex with an even number of edges A vertex with an even number of edges to it is an even vertex, such as vertex C from the previous graph. A vertex with an odd number of edges to it is an odd vertex, such as vertex A from the previous graph. A circuit is a path that begins and ends at the same vertex. A graph is connected if for any two of the vertices there is at least one path connecting them. If a graph is not connected, it is said to be disconnected. A disconnected graph is made up of pieces that are by themselves connected. Such pieces are called the components of the graph. As drawn below, we have a connected graph on the left and a disconnected graph on the right. A bridge is an edge that, if removed from a connected graph, would leave behind a disconnected graph. Example, a graph on the previous screen, if edge BD was removed, vertex D would be isolated from the rest of the graph. Euler paths and Euler circuits. A Euler path is a path that travels through every edge of a graph once and only once. Each edge must be traveled and no edge can be retraced. Euler path is an example here. And a Euler circuit is a circuit that travels through every edge of a graph once and only once. Like all circuits, an Euler circuit must begin and end at the same vertex, as it does in the drawing below. Euler's theorem. The following statements are true for connected graphs. If a graph has exactly two odd vertices, then it has at least one Euler path, but no Euler circuit. Each Euler path must start at one of the odd vertices and end at the other one. If a graph has no odd vertices, therefore it has all even vertices, it has at least one Euler circuit, which by definition is also a Euler path. An Euler circuit can start and end at any vertex. If a graph has more than two odd vertices, then it has no Euler path and no Euler circuit. Fleury's theorem. If Euler's theorem indicates the existence of a Euler path or Euler circuit, one can be found using the following procedure. If the graph has exactly two odd vertices and therefore an Euler path, choose one of the two odd vertices as the starting point. If the graph has no odd vertices and therefore an Euler circuit, choose any vertex as the starting point. Number of edges as you trace through the graph according to the following rules. After you have traveled over an edge, erase it. This is because you travel each edge exactly once. Show the erased edges as dashed lines. When faced with the choice of edges to trace, choose an edge that is not a bridge. Travel over an edge that is a bridge only if there is no alternative. This concludes the video for Chapter 15, Sections 1 and Section 2. Again, students, if you are in my MGF 1107 class, please do not hesitate to contact Professor Thronemuller to assist you. Thank you.